Thank you so much, Alexis, for this introduction. And I am delighted to be here and to introduce our new research project called Democritus, Decision-Making in Critical Societal Infrastructure. This is a research project in collaboration with various colleagues, both from KTH and outside. And I will mention soon about them in the presentation. And as you have probably recognized in the background of this picture, we have the School of Athens as portrayed in the Stanza della Segnatura in the Vatican with the various philosophers and of course including Democritus here. And the name of Democritus, it reflects a little bit the philosophy here behind this project and the complexity of today's world, and that now thanks to the digitalization and progresses in technology, we are having many important large-scale complex and networked systems, and often where communication, computation plays an essential role. And in these large-scale systems, such as water networks, intelligent transport systems, of course, telecommunication networks, smart cities in general, it's often so that the malfunctioning of IPs can have a catastrophic consequences. And the easiest to think, for example, is smart grids here. And in general, these very different infrastructures are coming from all the traditions of engineering, and one needs to have expert knowledge to manage them, to take optimal decisions about their operation. So then the result is that we need to take now sort of a new perspective to engineer these systems thanks to digitalization that has to offer new requirements in terms of safety, security, privacy, scalability. And so the idea of our research project is to contribute to the establishment of a new decision-making theory, especially about machine learning over networks. Of course, this is a huge undertaking, and we will only contribute to a part of these exciting research directions. And the name of Democritus comes from as my colleague Victoria was explaining after I came up with the name, after I proposed the name. The name it comes from that the philosopher wanted to find a common elements that describe or make it possible very different systems to exist together, the atomic elements. And we will try to see some of our atomic elements in the theory and research that we wish to study in this project. And one of the applications or one of the use cases where our research will be particularly illustrated is the area of water distribution networks. These are traditional large-scale critical engineering systems where the Internet of Things and digitalization is recently now starting to play an important role to do applications and functions such as early detections of leakages, early detection of contamination events, and also optimal management of the overall infrastructure with the potential great benefits for us as citizens, for us in the society, in terms of energy to produce water, to distribute water, in terms of also health safety. But again, this is only one of our application examples. And the general project is organized around 4 main tasks or work packages, from scalable learning and decision making to learning-driven networking, safety, security, and privacy. And then we have a task on experimentation. All the project is also taking benefit of collaborations and interaction with the Water Center at KTH, with Ericsson, the leading company, and also with the company that distributes water in the Stockholm municipality, Stockholm Vatten. My colleagues in the project, beside myself, is Professor Rolf Stadler, Professor Lars Kildehoy, who unfortunately is sick, and now we will have to look for a replacement. Professor Victoria Fodor, Professor Erik Sandberg, Professor Johan Karlsson, and finally we have Dr. Bent Algren from RISE, the Institute of Research in Sweden. And it's particularly here interesting also to mention that in this project, the participants are from various divisions, various departments and schools of KDH and even outside KDH, so that we will have a particularly stimulating intellectual interaction. And this is now a big overview, a quick overview on the project. And I would like at this point to focus on a particular research direction that I'm leading within this project. And is the research that we have called machine learning over networks. And also my little here request is that if you have questions, you are very much welcome to ask and to write them on the chat. And then from time to time, I will look at the chat when we have the section transition, so I will try to answer. But in general, my experience with Zoom and with this chat function is that it introduces some delays. So it might be that unless you are, it's really impellent for you to ask questions, you might wait for the end of the seminar. And of course, everybody is extremely welcome to contact me over email and for whatever other discussions. I also should mention that, by the way, tomorrow I will give an extended and longer version of this seminar for an invited PhD course at the University of Florence in Italy, which is also over Zoom. So those who are interested to the more technical arguments could even join that invited course. And the outline of this a little bit more technical presentation is this. I will try to motivate what is happening with machine learning and the Internet of Things. And then I will give a very quick background on machine learning and at the level that is suitable for coffee time as the one that we are having now. And after that, I will introduce some early results research-wise on this exciting emerging area of machine learning over networks. And finally, I will try also to give a tangible example of the impact that this research can have in big infrastructures and in the society. We start so with this interesting picture on the Internet of Things, which is arguably one of the most important current technological revolution. And I am particularly keen to have this kind of pictures, also because officially I'm professor of Internet of Things, and I've been working for a number of years in this domain. And it's exciting that the Internet of Things, that is the world of everything connected, an idea that comes from academic circles some 20-25 years ago, is excited that is now actually taking place in the real world with a tremendous economic impact. And I've taken this picture from the white paper available this year on the web pages of Ericsson. And they have divided the Internet of Things essentially in four main areas. One is the massive Internet of Things domain, where we will have many wireless devices, small wireless devices, to do applications such as monitoring of the smart grids, monitoring for asset management, fleet management. Then we will have the case of a broadband Internet of Things, where compared to the massive IoT, the number of devices is less, but here we will have higher data rates. Typically in massive IoT, you can think that devices will send a few kilobits per second. Instead, in the broadband IoT, we will have higher data rates to do, for example, autonomous navigation with drones, or to have the future services such as virtual and augmented reality. Then the other category of the Internet of Things that is now emerging these days, a critical Internet of Things, and in particular is the use of these wireless devices and methods to do, for example, autonomous driving, traffic safety and control, smart grid monitoring. And here the characteristic is that the communication and the latencies have to be extremely short and to support such critical infrastructures. And finally, another emerging area for the Internet of Things is the one of industrial automation, where we will have collaborative robots, advanced automation and control systems. Now, all this, although one can think that there are so many categories of IoTs, it's still true that every one of these categories is characterized by the huge generation of data. And often this data is distributed. It cannot be transmitted at a central location because of various technological or economic reasons. And so we are having, therefore, fundamentally new challenges to do data analysis that then will help a lot to understand about these very different infrastructures. Data analysis sometimes has to be in real time. If you now look at the historical evolution of various technological breakthrough that we have in the last 50 years, I have tried to put on the axis this a little bit now essential picture that illustrates the concept and idea. And here on the x-axis, here on the horizontal axis, we have various technologies that have succeeded one to the other. And on the vertical axis, the number of devices that often these technologies are supporting or are using. And we started by very few devices, such as big computers or network of computers, to more widespread devices, such as cellular phones and cellular communication network. And nowadays, we are starting to really have the realization of the Internet of Things, where we will have 1,000 devices per person. This number here has to be seen as the number of devices that we will have per person. Nowadays is already 5 to 10 devices to give an idea, but perhaps in 5 to 10 years we will have hundreds, and later perhaps even 1,000 devices per person in the world. And what is the situation is that if you look at the state of machine learning and artificial intelligence, everything is still conceived as if we were in this moment of the technological revolution, as if we were in this moment of history. But the reality is that we are rather in this moment here, where the connection between so many different devices, heterogeneous devices, is creating many new challenges. That, by the way, challenges that are common across various critical infrastructures, across various IoT use cases. And some of these challenges can be grasped from this picture here. Many of these devices will be small and distributed across various units that could be from cars to traffic lights in a smart city, or in the asphalt, let's say, or devices in the water distribution lines, in the sea and in the lakes, or devices in the various lines of the smart grids. And these devices, they have to be small and not too expensive, otherwise we will never be able to deploy the billions such devices in the real world. So they will have also, in general, they might have, in many cases, reduced computational memory and communication capabilities. And these devices also, they will generate data that is not easy to transmit. For example, energy communication energy reasons. We cannot easily send data from current IoT devices to central cloud centers. If we think, for example, to one of the most prominent IoT communication protocols, the narrowband IoT, it only allows to transmit a few kilobits per second, and instead often we would have megabytes of data that is generated per second. So it becomes technologically unsustainable and also economic unsustainable to move this data. Data still has to be distributed often near the devices or where it's generated. The current state of the art of machine learning is not yet aware of this distributed nature, of this heterogeneous nature of the devices, of the fact that they use different communication protocols, of the fact that the devices generate data having different characteristics, a different level of granularities in time and in space. And these problems, these technical problems of the IoT world are common to very many critical infrastructures. To summarize, we have prominent challenges when we try to do machine learning in the Internet of Things world, and this can be so quickly summarized in this little list here. We will have computational limitations of the devices. We will have a communication latency. It takes time to send data or to send the synthesis of data from the devices to some cloud or to some control center. We will have bandwidth limitations, and this is not just somehow a technological limitation, it's a fundamental limitation on every communication channel. We cannot send as much information as we like in whatever communication channel. And the devices often they have to be energy efficient. Also, we don't want to waste the amount of energy to do this huge data moving from one place to another place. We have also the great challenges that is emerging these days about privacy and security. If you think that the Internet of Things is collecting data about ourselves, it's private, very private data. We don't want that this data be used by some in some unintentional situation or for some malicious reason. And the same, of course, is security, another important aspect in the Internet of Things world, since these IoT infrastructures can greatly have an effect on our daily life. They still have to be secure, and we have to guarantee we have to have guarantees about the security of these systems. So what I'm claiming here is that, and of course also various other international researchers in this domain, is that these challenges are unsolved in the artificial intelligence world, in the machine learning world. The machine learning is still not conceived for the Internet of Things. And what we wish to do in this Democritus project, in this now particular subline of research, is to contribute to the frontier advancement of this domain. And we can briefly say that machine learning over networks is concerned with the problem of doing data analysis and machine learning tasks when the data is distributed across many different devices, and these devices are connected to public or shared communication infrastructure, such as the one of the Internet of Things, or even the current 4G communication system, 5G and beyond 5G. And we can roughly say that this emerging and exciting research domain is roughly characterized or divided into three main categories. And in each one of these categories, there has been some research performed. In some others, is much greener and fresh. And in particular, the three main subfields of machine learning over networks, or machine learning for the Internet of Things, is the communication efficient distributed machine learning. Then we have the design of new IoT protocols and methods for machine learning services. And finally, the joint design of machine learning and the networking. And in this talk, I will be putting particular emphasis on the wireless part of the networking, because it's closer to my own research. And also, we have so much to do in this research domain that before going to even bigger network, then the wireless is an enormous step. And there is so many tremendous challenges already when we consider wireless networks. And what I'm trying to do now in the next part of the talk, I will try to highlight some important concepts in these two main sub-areas and in their intersection. Let's therefore move to the next section. And since now we are having a coffee time, I've decided to give a pleasant, or if you like, a simple and gentle introduction to machine learning, but taking the main concepts that, although explained in this simplified introduction, they still give us universal insights. And I should start here in an humble manner, remembering to myself and to many that machine learning is a huge research area, and it's very different subdomains, such as unsupervised learning, which consists essentially in learning from data that are not yet labeled, where we have to find the distribution of data, for example. The other large category, important category, the supervised learning, where we already have some labeled data, and we might do some operations such as classification or regression. Then we have not yet another area, reinforcement learning, where there is a dynamic aspect with agents that learn continuously in time, and they reinforce in some manner their learning. And now this, I am very well aware, and I should apologize for those who are experts in all these domains that have been so rough and quick here. But this is just to give an understanding in this coffee time talk, that is a huge area and complex area with many sub-areas. So therefore, I decided to focus on the supervised learning part, and all the rest of this seminar will be about supervised learning. But again, the concepts will have still, and the concept and the implication in particular, they still have a universal nature. And in supervised learning, and a simple example is that the one here portrayed with this picture. We have a picture that is our data X, and then we have a function G omega of X or GW of X that maps the data X into a label. And the label could be, in this case, is this philosopher here in the School of Athens, is this philosopher Democritus or someone else? Is it Epictetus maybe or someone else? Well, this is here on the right hand side are the labels. Here on the left hand side, X is the data, Y are the labels, Democritus or Epictetus, and this is a function or a map that, as the name says, maps the data into the label. And supervised learning is essentially concerned with the design of this mapping function, which depend on, in general, this I have indicated with this W here, to say and to highlight that this is what we can choose, what we can design here to build such mapping function. And we will see that the Internet of Things world, the design of that function poses many new tremendous research challenges. To be more specific, let's have a data set D here, and this data set is a data set that we use to do training in our supervised learning task. In other words, this is a data set where we have some data xi, and we already know what are the labels associated to those data, the yi. We know that there is some function that is already there, and we know the correspondence between y and I and xi. And what we wish to do in supervised learning, in a sense, if I can say still in this rough pedagogical manner today, what we wish to do is to find a generalization when we get new data that is not part of this training data set. When we get a new data, X, how can we map this data into a label that is as close as possible to what would be the real label? And but we can use the data set D to design our parameter here W which is what we have to design such a good prediction function. Therefore, the natural question is, we have now to design to have a so-called a criterion. We have to have a method to look for this W and for the function, for the mapping function G. And the criterion is, as it is often called in machine learning, is the loss function, L. It's a criterion that helps us in looking for the good W, which in the end will give the G. And this is a function here that we can now generally call as f of W, and we will keep this f of W throughout this lecture. There is many ways to choose and to design this function. There are many problematic here to design this function, such as this is an approximation, this is an average over the losses of the various individual data. And so this becomes an empirical function, but it's something practical, and I'm keeping using it today to illustrate the important concepts. So in general, we will find the W by minimizing such a loss function, and therefore the supervised learning problem is equivalent to the solution to this optimization problem, minimization of the function f of W, looking for this variable W in a specific set where this variable has to live. And there is a traditional many ways to solve these optimization problems. And one of the basic, but still very insightful, is the gradient descent. The gradient descent is an iterative method that says that if we take the variable W here, and we update in the time t+1 equal to W of t minus eta for the sum of the gradients of the function fi, and this is done at time 1, 2, t, and so on. This is an iterative algorithm, and under certain assumption and with the proper choice of the eta parameter, this will converge to the solution to this optimization problem, which is the W that we were looking for. And this here, the number, remember, is the gradient, the derivative of this function with respect to the W. All this, it's nothing new, it's very well known, and it has been known for at least 300 years. Already Newton was working with these ideas, already using algebraic arguments, as we are doing now, with these notations. But I wouldn't be surprised if even the ancient Greeks would have arrived to these results using geometric arguments. So all this is very well known. And what is the problem here? The problem is that this kind of gradient descent algorithms and their numerous variations and complications, they are conceived to be run in a centralized place, which is in this point here. I mean, if you look at the history of technology, we are thinking to run that algorithm in a computer, or at the best, for example, in a data center where there is a set of powerful computers or servers that are connected with powerful communication network, typically optical networks, and they can easily perform the computation to solve this optimization problem, where computation is exactly this iterative updating. And again, this can have various computational complexity, but everything here is centralized. And in a sense, we can say this is the state often of the art of artificial intelligence and machine learning. But it's not this precisely what we need, since we are working nowadays here in this other technology, in this other technological revolution. And we have various problems when we try to solve this kind of gradient descent algorithms in the Internet of Things world. That's why people have started to investigate now already for a number of years methods such as distributed machine learning that can be seen as sort of fundamental and first step toward this area of machine learning over networks in general. Let's see how it works, distributed machine learning. Now, in the case of distributed data sets, such as what we have in the Internet of Things, what happens is that the data set that we have seen before is not any longer in a central location, but will be distributed across a number of devices. For example, this laptop, this iPad, this smartphone, and this other storage device. And in general, we cannot in the Internet of Things send data from these various devices to a common data center. And data have to be distributed. And they have to stay distributed for various privacy reasons, security reasons, energy efficiency reasons in the communications, computational scalability reasons. But yet, we are interested at solving the optimization problem that we have in machine learning in some manner without sharing the data. And this can be done if you look carefully at the function fw. It can be written as the sum of individual functions. So it becomes this a double sum. Before, in the previous slides, it was just one sum. Here now it's two sums, and where this is just a simple algebraic reorganization, where I've highlighted that there is an internal sum that depends just on the individual here devices. And I've called this overall internal sum as big F of K or W, where K is device K on capital K devices on the Internet of Things world. And this K in current cellular networks can be of the order of 20,000, by the way. Not to mention what that K could be in the future. Now, the naive approach here to solve this machine learning problem is to communicate the data from the devices to a data center and solve the optimization problem. And then the optimization problem finds a W, and the W is sent to all the devices, so the various devices can do their machine learning, can do their mapping images to images, for example, to labels or whatever other machine learning task. But again, remember, we have tremendous problems in terms of computational limitations with this naive approach. Communication latency, it takes time to send data. Bandwidth limitations, we have a limited amount of data that we can send at every time. Energy consumption of the devices, privacy, and security. So we need a method and a new theory, new methods, and therefore new algorithms, and even new hardware and software to embed all these technical problems into the ability to do machine learning for the Internet of Things world. There is a lot of history here in the recent years to do distributed machine learning, and which again means to distribute the computations of the optimization problem to the various devices that are involved. And I have here given a very short selection of some technical papers that are particularly prominent in this domain, such as the COCOA from Stanford and Berkeley group, the federated learning interesting from Google Research, and other methods such as the DNNC, Distributed Deep Neural Network over the cloud, the edge, and the devices, and FDML, a collaborative machine learning framework for distributed features. So this is just to give an idea of very prominent recent scientific contributions in the domain of distributed machine learning. But if we look now carefully at these papers, they can, these and many others, can be classified into these three groups. We have the case of where data is distributed across the various devices, and every device wants to do a machine learning task having the same model, the same W of the other devices. This is exactly what we want to do in this case with our smartphones, where our smartphone could have a very good W and to have such the GoW needs to in principle have data from all over the smartphones around, or even in an overall wireless network. Then we have another case, and this, by the way, is the case of federated learning. It's a celebrated distributed machine learning algorithm. Then we have the case of distributed features, which is another problem, the problem which data and features are not equally distributed among the devices. And then we have even a third case where the various devices need the data from each other, but every individual device is not interested to perform the same machine learning task as the others. And as it is said, we have distributed models here. So this shows that the area of distributed learning, it's very widespread and complex, and with a very different approach depending to the use cases. And here I would just quickly mention one of the most prominent recent results in this domain, which is the area of federated learning. And this is very interesting because it touches us in a sense. Every time that we can do advanced image recognition, let's say, or other advanced machine learning task with our smartphone, this is what in practice we could have implemented in the background. And here the idea is that if you now recall the gradient descent algorithm that I just introduced to you before, you recall that we start from noting that the overall loss function to do the training is a sum of local function, fk, that belong to this device, this device, these devices, and this other device. Then what the gradient descent does is that it adds a local computation at the device k, which I've written here in this equation, and in other words, every device does a local computation of the model W using the local function fk. This is the gradient of the local function, and this is very similar to the gradient descent that we have seen before, except that we are using only local information embedded in the function fk. The data that we have available to do the training is embedded in the function fk. Then what we do, the device sends the model wk to the cloud here, to the central point. The cloud does an average in this manner of the models of the various devices and sends back the averaged model to the local devices. Everybody keeps doing this iteratively, and in the end, it's possible to show that under a certain assumption, this algorithm converges. This algorithm is particularly appealing because it has various properties that are in this direction of the Internet of Things world, such as the data never leaves the devices, although there can still some privacy leakage and security problems, since from the transmissions of the WK from the devices here to the cloud, sometimes it's possible to reconstruct some information. And there is a huge research here, for example, in this domain, how to keep private and secure these computations. I have many colleagues here in KTH who are working in this exciting domain. For example, I can mention my colleague Tobias Oktering or Mikael Skoglund in the intelligent systems department who are concerned with this kind of technical questions. But what is now interesting is that so far, if you have been attentive, apart having data that is distributed, there is not much more about wireless networks and communication networks, and they all play a major role here, since we will not be able always to send these models. We cannot send sometimes at all the models, but even variations of those models. And so this is federated learning has to be seen now as one of the most advanced area in distributed machine learning, and still is unaware of is still not fully aware of the communication issues. So therefore, the result is that this kind of distributed machine learning algorithms are still conceived for this case. This is not yet the Internet of Things world. Even the iterations here of federated learning, and there is nothing that is really communication network. There is nothing that is wireless. So yes, it's true that they will solve the computational limitations of performing machine learning tasks, but distributed machine learning still have communication latency problems, is not solving bandwidth limitation, is not solving energy consumption, is not really solving privacy, is partially addressing security, and in the end, if we execute them in the Internet of Things world, the performance will be pretty bad. So we need something more. And what is this here, the great now novelty, or the great research challenges that we have ahead of us? Well, first of all, is the creation and the design of methods to do communication, also wireless communication, particularly for machine learning services. And the rest here this section of the talk that I'm giving to you now is based on a paper mainly authored by Eric Elstrom and Milton Barros, who are two young researchers in my research group. You can Google easily. This is wireless for machine learning that is on arXiv. We have uploaded in September 2020. And here the idea is this. If we look at traditional communication methods and systems, the communication resources are dedicated to individual transmissions. So in other words, when we look at the gradient descent like algorithms, the data transmission will happen using some slices of time for a given frequency. First, we transmit the model for the device 1, then the model for the device 2, then the model to the device k, and then we restart again in time. Or what we could do traditionally is that we have channel frequencies, and over a specific slice of frequency, we send the model of device 1, then the model of device 2, and then the model of the device capital K. And note that these models here can be many gigabytes of information, by the way. So it can be very small, but also very big, depending on the machine learning application. But if you've been be a little bit attentive for what we have seen so far, all the gradient descent-like methods, they will need a sum, the sum here at the fusion center, at the cloud center, the sum of the various weights here, of the various models of the individual devices K. And this means that we don't need to send actually the individual Ws of a communication network. We can send them all together, in a sense, if we have a common shared communication network, because the network itself will perform the sum. And this is pretty natural to think. If it is like if we are speaking, if various people are speaking at the same time, then their voice will be heard at some point as the superposition of all their voices, right? And the same is with the communication of a sum of many channels, not only wireless channels, but also wired channels. And the result here is somehow groundbreaking in the sense that the communication channels and systems, such as the current wireless networks, are all done to have individual separated transmission. But when we will have machine learning services, artificial intelligence services in the wireless networks in the future, in general communication network, we don't need to have such assigned channels, but all the involved device can talk at the same time and in the same frequencies with tremendous energy and communication efficiency savings. So this is portrayed here. That is the great novelty, the frontiers of research, that is the true wireless and communication networks for machine learning services, which will apply in this domain. But of course, this kind of these research ideas and research questions now we are very early in time. They have been around for some year, a little bit in the background, but there has not been yet the full realization that they can be so important. In fact, many are even wondering whether this will be interesting and so useful. To have such a fundamentally new, such fundamentally different, such groundbreaking new physical layer, medium access control and networking methods to support machine learning services. And that's not the first time when we are in front of such great novelties that we have people who are skeptical. And here I have some famous historical skepticism, such as when in 1876, the chief engineers at the British Post Office was evaluating, were introducing the wired phones. He answered, no, we don't need them, because it's the Americans who need these telephones. We have so many messenger boys that can transmit our messages. So we don't need such groundbreaking, such new technology. And a few years later, just to stay in the area of communications, it was a young Guglielmo Marconi, the Irish-Italian Nobel Prize and inventor. He proposed his system to do wireless communications in the year 1898 to the Minister of Post and Telecommunication, actually telegraphy in Italy, Pietro La Cava. And he answered, I think you must be crazy to think to such foolishness. And we can go on here with the history of when we introduce this kind of new technologies and ideas. One is also about the father of the cell phone. In 1974, he said that I think that the cell phones will absolutely not replace local wire systems. And we know what is the reality today. Of course, we have many more such a skeptical approach to wireless and general communication for new fundamentally new services. And I can include also myself among, more humbly, of course, among various skeptical people. In 2005, I was still very suspicious about neural networks, and today I'm heavily working with them. So the question is today is we will have really wireless for machine learning. Well, historically, it's probably we have some interesting convincing arguments, since we have had communication systems for specific use cases: voice, unicast, multicast voice, broadcast video, multicast voice, multicast data, and lately wireless for multicast multimedia services. So why not continuing the specialization of communication systems to new groundbreaking services such as artificial intelligence services? And I strongly believe that this will be the case, that we really need a new technology to support this kind of future services, especially for the augmented and virtual reality world. And what is also fascinating is that if we overcome our skepticism about the need of communication systems for machine learning, then there is also the natural consequence that we will need to jointly investigate the design of networks and machine learning at the same time. And we have started to work with that, with this exciting area called the co-design of wireless and machine learning. And I have a few here, I would have some technical results that I would like to very, very quickly mention. And those of you perhaps who are working in this domain could have a look at these papers. I don't have much time, but I would like to, since I have to finish by 4, and I have to give you also possibility to ask some questions. So let me mention quickly that we have a very recent result that is precisely in this new wave of co-design of the Internet of Things and artificial intelligence. And this is the Internet of Things as a deep neural network, mainly authored by a former PhD student, Rong Du, who is now with Ericsson, and Sindre Magnusson, who works as a former PhD student of mine, has been just hired as associate professor at Stockholm University. And you can have a look at this paper if you are interested. And I would like just to quickly mention that this is one first attempt to the joint design of IoT and machine learning with very promising results, especially to the water domain. I don't have time again really to look at these technical results, but we have applied it to the iWater projects that I mentioned already to you earlier. And another extremely interesting activity in this joint design of networks and machine learning is in this couple of papers authored by Afsaneh Mahmoudi and Hossein Chokri Gadi-Kolei in my research group. And again, those who are interested, you can have a look. And you shouldn't think that this research direction is of little interest, because if you don't care about machine learning for the IoT world, and if you don't care about doing right IoT systems for machine learning, you will probably experience poor machine learning performance in your business. And of this I'm convinced, and I could give more technical arguments about that. I don't have the time, but I would like just to quickly conclude with the significance of this research about critical communication networks, where already now and later more in the future, we will have this fundamental infrastructure, communication infrastructure, to do real-time services such as intelligent transport systems, augmented reality for entertainment, distributed interaction at the sense level, at the sensory level, even surgery over communication networks and wireless communication networks. On these proceedings of the IEEE, we have given an overview on this exciting domain. And if we will be able to embed here also machine learning services and the joint design, the fundamental understanding of machine learning and the communication network, we will be able to do, as we have already started to do, and to have very, very tangible services such as Internet of musical and audio things, where people could play together, could play music together at different locations, as if they were in the same room. Something that is starting to be possible only today, thanks to this advancement of the Internet of Things and machine learning over networks. And in fact, I'm co-founder and scientific director of a company called ELK, which is making all this possible. And we are arguably among the first in the world to have performed a real 5G concert where the players were connected among them using a 5G network. Those who are interested to know more could look at this ELK Audio website, and I would like to give now a little indication of this, what is actually possible. And so we conclude our seminar. Let me give this video, and I'm trying to share again. Just a little bit of patience. Okay, can you see the video, by the way? Can you please tell me?
Yes, we can see.
Very, very good. Very good. Thank you so much. And this concludes the presentation. And I should thank very many people here in my group. I would like to just show you some of them, of the current group, such as Afsaneh, Enric, Shashi, Hussein, Mailton, Thomas, and Kian. And this concludes my presentation. If you have questions, I'm extremely happy to take them now. And feel free also to contact me over email.